Yeah, we can start? OK, great. Hello. Great to see you here. My name is Adam Warski. I come from Warsaw, Poland. And I would like to talk about the dependency injection in Scala. I think there's definitely a couple of approaches which you can take, and probably you read around on the internet. You can use constructors. Some say that the reader monad is a replacement for all dependency injection frameworks. On the other hand, we have Play, which uses Juice by default. So maybe I would like to try to clear up some of the confusion, which construction and which abstraction to use when. So there will be like 4 slides, and then we will do some live coding. Let me know if you would have any questions throughout the talk. Please let me know. I will try to clear things up. OK, so let's start. So first of all, maybe you're familiar with the whole dependency injection thing, maybe not. So just to set some common ground, probably if you come from Java, you have heard the term. But like not everybody comes from Java, luckily. So maybe that introduction would be useful. So in dependency injection, imagine you have 2 services. These services are usual classes, but let's talk about services right now. And one service calls another service, right? That's quite a common scenario. So one service is a dependency of another service or a client. So with dependency injection, what we want to achieve is we want to decouple these 2 services, right? We don't want one service to be aware of how the other service is being constructed. It just wants to use it. It doesn't want to know how to build the service, how to create it, right? Dependency injection also implements inversion of control, right? So the service doesn't know how to create its dependencies. It just wants to use them. And this has a number of benefits. So the first being probably hiding implementation details, right? So one service doesn't really know how the other service is implemented. What it should only know is how to use the interface. Other benefits include testing. So you may want to swap services for testing, use a mock implementation, a stub, or something like that. Also, dependency injection helps with separating concerns. So usually creating a service, creating a class is a separate concern than actually using it. And it also helps you to organize codes, especially if you have like business-like code, let's say, with some complicated business logic. These patterns help you to organize your code in a readable way. And there's a couple of ways, like especially if you are coming from Java again, you probably know these. You can either pass as to how the dependency injection is implemented at the code level. So you either use constructor parameters. In the older times, you also use getters and setters, but probably nobody does it that way anymore, luckily. Or you can use a service locator. There's also a possibility. So we have like one global object where you can register services and then ask for services back. So what I would like you to get out of this talk, and hopefully I will succeed, is convincing you that you don't really need anything special to do dependency injection. Because in its essence, dependency injection is just using parameters, class parameters, method parameters. So that's a construct like we all know. So you don't need any libraries, any frameworks. The libraries and frameworks can help you in some cases. So they certainly help you in avoiding to write new anywhere. But they are like not mandatory to do that. They bring on some additional features, and you should really only use frameworks if you need those additional features. They aren't like, if you are bootstrapping a new project, probably you don't need any of them. So before we start coding, just so that you know who's talking to you. So as I said, I'm Adam Warski. I'm a co-founder and software engineer at Software Mill, which is yet another software Scala consultancy based in Poland. We do custom software for clients, mostly from the US and from Western Europe. I have some open source projects like MacWire, which kind of, that's where my interest in dependency injection come from, because it's a library for DI, ElasticMQ, QuickLens, and a couple of others. I write blog. I write some blogs, and I have a Twitter account, which probably isn't this surprising nowadays. OK, so on to the coding part. OK, so we will be dealing with cooking on a very basic level. So we will build 3 abstractions, one on top of another. So first, we will have a KeyValue Store, which is already written here. The KeyValue Store is quite simple. It supports basic CRUD operations. So we have a create, read, update, delete, like what you would expect, right? Mostly. This implementation is in memory, but you could imagine that it could be another implementation which could write to something more fancy, like a real database. We are ready for that because we return futures everywhere. So we are ready to be reactive. That's like the first step. So this implementation is quite simple. We just use a concurrent hash map as the background. So that will be our first abstraction. So the second thing the second level that we will build on top of this KeyValue storage will be food storage. Okay, so we will build a food storage, and on top of this food storage, we will then build an abstraction to actually combine the various ingredients and cook some food. Okay, so the food storage will operate on some primitives. I will just alias them over here so that the code will be more readable later. So we'll have food name, which is a string. Food quantity will be an int. And the food KeyValue storage will be KeyValue storage from food name to quantity. Okay, so our food storage will be basically a kind of a map from food name to quantity. And we will have like 2 basic methods which operate on the food storage. So we can add some food. To add some food, we need the food storage. We need the name of the food and the quantity. And this gives us a future unit. So that's a purely side-effecting function. Okay. So to add some food to our storage, what we will do is we first read the current amount that we have. So we read. Now we do calculations. So the new amount is simply we add the current, add the given quantity to the current one. Or if there's none, we just add the past quantity. And finally, we update. Update and updated. Okay, and we yield a unit. Okay, so that's a very simple method. Similarly, we can add food. We can also remove food from the KeyValue storage, given a name and a quantity. Now the result here won't be a unit. It will be actually quantity, because we may remove a smaller amount than requested, right, if there's not enough. So again, we read the current amount. And now we do some very complicated calculations, because we have to calculate how much we can actually get. So in stock is current or 0. Taken will be, now that's the complicated math minimum in stock and quantity, right? And left is in stock minus taken. And now we update if left is greater than 0. Then we update it with what's left, our storage. Otherwise, we remove it altogether. Okay? And we return the amount that we managed to take. Okay, so now we have, on top of the KeyValue storage abstraction, we have built another abstraction that's food storage, right? We can add a given quantity of food and remove some food from it. Okay, so far so good, nothing very fancy. I hope that's That's nothing complicated. So now, on top of that, we will build yet another abstraction, and that will be used to combine ingredients and cook some food. Okay? So we will define a cook sauce method. We will be cooking pasta sauce. So let's say we want to cook a given amount of sauce. So now, what we will need? So what do we need to cook sauce? Well, to cook sauce, we need a way to obtain ingredients, right? And in the end, when the sauce is cooked, we need a way to put back the cooked result. So what we need is a method, one method, take food, which takes a food name and quantity and returns a future quantity. That's how much we managed to remove. That looks similar, but it's not exactly what we have implemented before. And we need another method, add food, which has a similar signature. So it takes food name quantity and returns a future unit. So a purely side effecting function. OK. And as a result, again, we return the quantity of sauce that we have managed to cook. OK. So how do we cook sauce? Well, we take some tomatoes, right? Take food, tomato quantity. We take some other vegetables, non-tomato vegetables, same amount. We also take some garlic. Garlic's always good. Garlic, half. We take twice the amount of garlic that we actually need. Now we calculate how much sauce we have cooked. And that's tomato Q divided by 2, because some of the evaporates, and vegetables times 3/4. And finally, now we have cooked the sauce, so we can put it, like we put back whatever we have cooked into the food storage using our add food function. So we put back the sauce and the quantity given. OK. And we yield the sauce quantity. OK, so now we have built like this method. It knows nothing about food storages. It knows nothing about KeyValue stores and so on. It just takes some methods as parameters, right, which allow it to operate. So, so this method, to actually be able to cook sauce, to prepare the sauce, it needs the take food method to retrieve food and the add food method to put it back. In a similar way, we can implement a cook pasta method, right, which works exactly the same. It uses different ingredients because it's pasta, not sauce. OK, so now we have these two methods. So all looks good. So now we have to actually use them in an application to be able to test that things are working. So one thing that we will need for sure is we will need an instance of our KeyValue store, right, which we'll use throughout new. We will use it throughout our example. So now I will just prepare, copy-paste a snippet. So first, we need to populate the KeyValue store with some ingredients. So let's say we go shopping, we buy some tomatoes, vegetables, garlic, and so on. So that's we are calling the add food method here, which updates our KeyValue store with the ingredients, right? That's shopping. And now we can implement cooking. So for cooking, what we do is we first go shopping. Then we cook some sauce. So to cook sauce, what we need to do. So let's say we want to cook 5 sauces, or 5 of sauce, whatever the unit is. So now we need to pass in the take food method, right? The take food method in cook sauce, if you look here, it takes a food name and quantity, right? It doesn't know anything about the KeyValue store, and there's no reason why it should know anything about the KeyValue store. So what we do is we pass in the partially applied take food method, which we have, add food method, which we have implemented earlier. Okay. So we are passing the KeyValue instance that we have defined here. And similarly, Sorry, that was remove food, sorry. Remove food and add food, similarly partially applied. Okay? And in a similar way, we can cook pasta, and we cook 10 pasta because we like a lot of pasta, and we yield some string just to see the results, that it actually works. Pasta. And to be able to run our program, we will eat things. So that's await.result. Results. So cooking, it's very fast cooking, only 1 second. Print line eating. OK, hopefully this will compile and run. Yeah, you can see that it compiles and runs. OK, so so far what we have done, we have implemented, so we have one basic abstraction, which is the KeyValue Store. On top of that, we have the food storage, which for now takes the form of 2 methods. Right? The methods take a KeyValue Store and operate on it. And finally, we have the third level, which is the cooking level. Here we take as parameters the methods which operate, which allow us to take food in some way, right? And finally, when we actually want to run our application, we have to pass in the dependencies to the appropriate functions. So far we have used only functions, nothing very complicated. OK. So by the way, like in a real application, all of these sections would be in separate files. Here I'm having it all in one file just for a demo. OK. So now, well, we are not happy with our code so far. We want to improve it. So we have spotted that there are some things, that there's some repetition which we would like to eliminate. So for example, here, the KeyValue parameter is common for both methods, and we actually decided to extract it higher, and we decide to create a class fridge, which will take the KeyValue parameter, the KeyValue storage, and so that we can use it in both of these methods. Okay, so we have extracted some of these parameters into one level higher. So now we have a class with 2 methods, and what this class is parameterized by our KeyValue store. So in a way, you can think of these methods inside these classes as being partially applied functions, right? Because if we have an instance of fridge, we have the first parameter here, right? So it's already like partially applied, so that we can use these methods over here. So now, why did we extract only the KeyValue store and not the food name and food quantity? Well, the role of the parameter is a bit different, right? The KeyValue store is kind of a service type parameter, right? And it's probably going to be fixed for the duration of the operation of our application. And these are more data-like parameters, right? So they are going to change from invocation to invocation. So that's why we have decided to split the parameters this way. OK, and in a similar way, we can extract these 2 parameters here, right? So we could create a class which had the take food function and add food function as parameters, but we noticed that these signatures are exactly the same as the methods over here, which is a very lucky coincidence, because we can now extract a class, take a fridge as a parameter, and remove those ugly functions, those ugly dependencies altogether. Okay, and fix the code, of course, because now we don't have like direct access. We need to go to the fridge and take the food or add food. Okay, so we have extracted some parameters over here. So we have moved the parameters to class parameters, right? So we have created like classes are like wrappers for methods which have similar functionality and which have similar dependencies. So now what we need to do to actually why doesn't this compile? Because it's not take food, it's remove food. So now what we need to do is we need to update our end of the world code, right, where we actually bootstrap and run things. So we need to create a new fridge. It takes the KeyValue Store as a parameter, and we need to create a new cooker, which takes a fridge. And now we have to do some small changes here. So we add we call this on the fridge, right? We have moved the parameter from the. It's no longer the first parameter of the method, but it's a method on the class. So that's not a very big difference. And here we call methods on the cooker and remove these dependencies over here, because these dependencies already passed at construction time over here. OK, so our code hopefully still works. Yeah, still compiled and worked. That's very nice. OK, so now what we have done is we have noticed that some of the dependencies are common for the methods, for the fridge methods and for the cooker methods. So we have extracted them as a class parameter, right? And also, like, we have noted that there are like two kinds of parameters. These are like the service type parameters, and these are like more the data like parameters, right? Similarly here, the fridge doesn't change it's always the same parameter like throughout the operation of our application, but the parameters here do differ from invocation to invocation. OK, so now to complicate things a bit, we will create an IoT-enabled fridge. So let's say we have a new we have a new dependency. So we will have an IoT trait, just to show you how we can add more dependencies. The IoT is very simple. It only allows you to notify users with a message. We will have a default implementation, cloud IoT gateway, username string, password string, and it implements IoT. And it will just do a future successful print line sending via cloud the given message. OK, so now our fridge, so we have a very simple IoT service, right? So now we want our fridge to be able to use this IoT service. Again, it's a service type parameter, so we add it like to the common parameters in the class, and now we can use it anywhere we like. So here we can say IoT dot send notify user that a given quantity of a given thing was added to the fridge. And here we will say that it was removed from the fridge. OK. So now we are almost done. If we try to compile, we will luckily get a compile time error. So here we have an unsatisfied dependency, right? So that's a good thing of actually using Scala for these things, because you get compile time errors. You don't, like if we use juice, for example, right? We will only get a runtime error that the dependency is missing. So we need to create the IoT dependency. So we do just that. Cloud IoT gateway, username Scott, password Tiger. OK, and now we can use it here. It's an Oracle gateway. So we can use it here. So this will almost work, except that at the moment when a fridge is constructed, IoT will still be null, right? Because these are vals. So there are two ways to fix this. One is to use IntelliJ. Well, three ways. One is to use IntelliJ. You will get a warning. The other way is to manually construct these in the right order. And the third way is to use lazy vals. And that way, the right order will be figured out for you automatically. So you don't have to use you don't have to worry about that. And now we can try running it, and you can see that we are getting some IoT notifications every time something happens to the fridge. OK, So now what we have done here is from like the new things, we have added a new dependency. So now our end of the world code is getting a bit bigger, right? We are when we actually want to run the application, we have a section where we create the object graph, right? So here we create the object graph, which is kind of more or less static throughout our application, right? Because these don't really change. These are the services which are wired together, and they operate later through, like when your application works. So we have a section where we create the object graph using Scala and lazyvals, and then we can use it to do actual work. Okay, so that's like so what we have here is the constructor-based dependency injection. As you can see, it's quite simple, right? It's just using one step from using methods for everything and passing around functions. But that's not very convenient because you get a lot of these function parameters. So we can use the constructor-based dependency injection to actually make our life a bit easier. So now let's jump to the second part. So let's say we have a change of heart. I just need to update my notes. Okay. Let's say we have a change of heart, and we actually want to track exactly when we access the KeyValue Store. So if we look up here at the addFood method signature, well, it returns a future, so we kind of suspect that there's some asynchronous things going on in the background, but we don't really know what kind of asynchronous operations, right? The future is completely opaque. So let's say now we want to track exactly when we access the KeyValue Store. So before, this KeyValue Store was an implementation detail of the fridge, right? So if we look at clients of our fridge class, like the cooker, right? It has no idea that fridge is implemented using a KeyValue Store. Okay, so that it was an implementation detail, and we achieved that using a constructor-based dependency injection. But now we have a change of heart, and we actually want to make it explicit, that we want to make it visible in the method signature, that whenever you use a KeyValue Store, you want to have it in the signature. So what we will do is we will remove the parameter from here, and we will move it to the method signature. So, but we won't add it to the method parameters, but instead we will return a function so the result of our method will be a function which needs a KeyValue Store to operate and returns a future. Okay? So as we return a function here, well, we need to return a function, right? So what we do is we take a parameter called fc, and then the rest of the implementation is unchanged, right? It's a function. We take a parameter and return some results which uses this parameter. And we do a similar thing over here. Okay. So again, we have moved the dependency from the constructor to the result type of the method. Okay. So far it's not a huge change. However, if you look at the signature of the addFood method, you can now, with a high degree of probability, be sure that you have a future here because a food KeyValue Store is used, right? Well, most probably the KeyValue Store parameter is here because it's going to be used at some point. So you have that the side effects in the addFood method are due to using the KeyValue, at least in part. Okay, so now this code won't compile because we have the clients of the fridge, right? Right now the remove food method returns a function which needs a KeyValue Store. So we need to take the KeyValue Store from somewhere, but we don't have it, so we will return a food KeyValue, a function here as well. And we will do the same changes as we did before. So now we need to change our code a bit. So now in the cooker, the KeyValue store stopped being an implementation detail of the fridge. Instead, it's now an explicit dependency, right? Because we want to track which methods use the KeyValue store. And indeed, the cook sauce does need a KeyValue store to operate, right? It does have that effect because it uses the fridge. So we will return a function here. So we take, to implement the function, we take a parameter, and we pass it on to whatever the fridge method return, right? So the remove food method, that one, now returns a function which takes a KeyValue store and then only gives the result. So to get the result, we actually invoke, we actually use, we actually invoke that function here. And the same happens over here. Food KeyValue. So FC. And we have to pass in the parameter over here. OK? And finally, so we have to fix our graph creation code. So we remove it. We remove the parameter. And we have to add the method invocations everywhere over here. So this isn't very nice, but we'll fix it in a second. And over here as well. OK, so now it compiles again. OK, so now what we have achieved, what we have changed, we have moved the KeyValue dependency. It's no longer an implementation detail of the fridge. But it's something completely opposite. It's an explicit dependency for which we want to track usage, right? So we need to know exactly which methods possibly transitively touch the KeyValue store. So now we know exactly which methods. So we have kind of effect tracking, right? It's like an effect tracking system. OK, so now this code isn't very pretty. So we have all of these function invocations over here. So how can we make it nicer? And here comes in the reader monad. So the reader monad is just a fancy name for a function, sorry, like that. OK, so the reader monad is just a case class, OK, which encapsulates a function for a fixed first parameter. OK, so the reader monad is a case class which wraps a function. And so just to be precise, we need to add the type parameters here. And if we fix the first type parameter, so if we fix t and only vary the second type parameter, this will form a monad. So what does it mean in practice? In practice, it means that you can use the for comprehension to combine a series of such constructs. Okay? In fact, we will use a slightly more advanced variant. So we have also the reader t, which has 3 type parameters, tu. And it wraps a very similar function. So here, the reader t, it's also a monad. And it wraps a function which takes a parameter and returns a wrapped result. Okay? So the wrapper, for example, can be future. Right? That will be the wrapper in our case. And that also forms a monad if f is a monad. Okay? So to combine the results, it will use however f is combined later. OK, so that's if you look at this function, right? It's exactly the same shape as the one over here, right? So we will wrap the functions that we return from these methods into the reader monad, and this will allow to make our code a bit nicer. So what we will do is we will return a reader t, future food KeyValue store a unit, and this means that it wraps a function which takes a food KeyValue store and returns a unit wrapped in a future. Okay, so maybe I will just write it in a comment over here, just so that it's clear. Is a method, it's a function wrapped food KeyValue store future unit. Okay, and well, to create the wrapping, what we have to do is we have to create the case class instance, right? So we simply write reader t. That's the constructor of the case class, right? And then we pass in the function, okay? As before. So no changes. A very similar change over here. Only we return quantity reader t. Okay, and just to get the braces right. Okay, so the remove food, maybe I will make it like this. The remove food, again, it takes the case class constructor and wraps a function. Okay, so far so good. Now let's proceed to the cooker. So now the cooker, well, over here, these methods now return not functions, they return the wrapped functions, the reader t instances, right? So we would like to use them. I will just copy that. So we notice that the function that we return here are also the same, like the same shape. So we can also probably return the wrapped version. That's what we will do. And well, we could simply wrap the function, and so we could simply write reader t over here, right? And wrap the function and then unwrap the results that we get here and invoke them, but that would be just more manual work. Instead, what the reader monad allows us to do, thanks to the part that it's a monad, we can use it in a for comprehension. So we can remove that parameter, and we can remove all these invocations. So what the reader monad does for us, right? So that what the flat map implementation in the reader t does, it invokes all the functions as we combine them, right? So here, like before, you can see it below here, we have manually created a function and then invoked all of the dependent functions with that parameter. The reader monad does it for us automatically, right? So we no longer need to return the functions. We can just compose the reader monad instances that we have obtained here. Okay? So the code, again, looks much nicer. We don't have all that noise with the function invocations and so on. But behind the scenes, it works exactly the same. It will be a function that once provided the key value parameter will invoke first this function, then it will invoke this function with the passed-in parameter. Okay? And that's the monad part. Which essentially means that we can use that in a for comprehension without that noise. Okay, and we also need to change some things down here. So before we had again those function invocations, which were just boilerplate. So we can remove all of them because now we can combine all of these methods. The add food method, they return reader instances, so we can simply combine them into one big reader instance, which when applied to a parameter will apply all of these in a sequence. Similar over here. Although, like one thing you don't really see behind the scenes, right? If we explicitly call the functions here, this has type future of quantity, right? And now if we remove these, we get the reader t of like these parameters, right? So we get a slightly different return type. So our cooking value is now a big reader instance, right, which wraps a function, which when applied to a parameter will run all of our code in sequence. So we can't really use cooking in an await result because it's a reader, not a future. So what we need to do is we need to actually unwrap it. We unwrap it using run. If we go to the source, you can see that it's a case class, which is called case, not reader t, but it's the same thing, don't worry. It's a case class, and it wraps. It has a single parameter, which is a function, just as I told you. So that's exactly what we have, right? And that parameter is called run. Okay. So to unwrap, to get the function from the reader monad, we just call run, and we provide the parameter, and it hopefully should work just fine. Okay. So 5 minutes. That's not a lot, but we are almost done. Okay, so the crucial difference here with the reader monad, we don't really do dependency injection, right? Because we don't, there's no dependency hiding. We don't hide the dependency. Quite the opposite, we make it explicit. Okay, and so there's like quite a crucial difference between these two. Dependency injection hides your dependencies. The reader monad makes them explicit, and they're both useful. I guess that's the good part. You can use both constructor-based or whatever-based dependency injection and the reader monad, but for different things, right? So here in our example, we still have the IoT dependency hidden, right? Clients of Fridge have no idea that the Fridge uses the IoT dependency, right? But they are very well aware of the fact that it needs a KeyValue Store to operate, because we have decided to track it as an effect. Okay, so you can use the reader monad to track effects in your code, and you can use constructors, also known as dependency injection, for hiding dependencies. So now probably I should also, if you've been to Martin's keynote, he had a whole slide on why the reader monad is bad. And it's true that you could do the same with implicit functions. Well, you will be able to do that with implicit functions in Dotty. However, the important thing is that this will be like in 3 years when Scala 3.0 is out. And so until that happens, you can use the reader monad for the same, to implement this kind of effects tracking. So I agree that the implicit functions syntax is nicer and more lightweight, and also faster because you don't have to create the reader wrapper, but it's not yet available. So for the time being, we have to live with the reader monad. Okay, so I guess that's also the main point of what I wanted to show you, is that you can have both constructor-based dependency injection and use the reader monad. In fact, you can also combine the two. If I will just jump to a bit more developed example. So here, let's say that we have modified our example so that we have a KeyValue Store trait, right? And two implementations in memory and cloud. Okay? So now, when we want to track the effects that somebody uses a KeyValue Store, we just want to track the fact that a KeyValue Store is used, not which implementation. Okay? So we can use, as before, we use the reader monad to track the effects of using a KeyValue Store, but not any specific implementation, just the trait, right? And if we go now scroll down, and here's our end of the world configuration where we create the object graph. So when creating the object graph, we can actually use constructor-based dependency injection again to create the dependencies like over here, right? Which we then pass on to the reader monad. So this all like fits together. Okay, so just to sum up, you can use, and you probably should use, constructors and constructor-based dependency injection, or constructor parameters, however you want to call it, to hide implementation details. You can use the reader monad to make dependencies explicit and track effects. And they are both useful, and they can work together. So what about frameworks, right? And what about libraries? So frameworks give you a short-term profit, because when you start your project, you don't have to worry about writing this, wiring this object graph. But you, well, and it is handy. It is like nice. You don't have to write all these new invocations and so on. However, you give up a lot of control in exchange, right? With the pure Scala approach, you can create your objects as you like, in any way, basing on configuration, basing on the environment, using new, well, it's just code, right? When using a framework, you commit to doing it the framework's way. So that's why I would always start with a clear, with a pure Scala approach, and only later maybe add a framework, which can have their benefits, right? If you need AOP, if you need interceptors, if you need scoping, that's when frameworks can be useful, but that's usually only in a later stage of the projects. So some libraries and frameworks to look at. Well, there's MacWire, which is mine, and of course the best. That's not a framework; it's a library which helps you to create the new to create the object graph. So you don't have to enumerate all the dependencies. It generates the new invocation for you. There's Grafter, which also combines the reader monad and constructor-based dependency injection in a slightly different way, so I encourage you to take a look at that. There's Juice, which is by default used in Play. However, if you're using Play, it's very easy to switch to compile time dependency injection using constructors. There's a whole section in the documentation on how to do that. It shouldn't take you more than 5-10 minutes to remove Juice and use compile time dependency injection. And there are some service locator implementations in Scala as well, for example, Scaldi and SubCut. OK? So one last slide with a thank you for your attention. The code for the presentation is available on GitHub. And yeah, that's it. Thank you very much. And I don't think maybe we have time for a couple of questions.
So I haven't seen MacWire. I've seen Grafter before. Does MacWire kind of use macros to generate reader monads, or is it more?
No. So the only thing MacWire does is it generates this piece of code. So you don't have. So if you have 5 dependencies here, you don't have to enumerate them. It's a macro which, based on the current environment, generates this new invocation for you. And that's useful, when you add dependencies, move them around, you don't have to update this wiring code. So that's all it does.
How would the reader monad scale up to having multiple effects in a single function call?
So if you have multiple effects, well, you would create probably a case class which would combine them all, right? The tricky part is if you have one function which has effect A and another function which has effect B, so you have to kind of glue it by hand. So that also will be nicer with implicit functions because, well, yeah, that's the way they work. OK, so I'm here until the end of the day if you would want to catch me, or you can mail me or write me on Twitter or however else. So thank you very much again.